Let's look at a basic statics problem, a distributed load on a cantilever. So in this picture, you want to first analyze the diagram and see what information you can get. Well, just visually you have a wall with a fixed connection of a beam, slender beam that just goes straight out, distance L. Notice this arrow here with an X just indicates the direction in which we're thinking positively. We've notated a distributed load where you have a straight line and just arrows here, and that just indicates that over this entire body you'll have forces dictated by this equation, so Q of X. So at any point X you're going to have Q1 load. So Q1 is all of these arrows. And also we've notated 2 points A and B, which might be of use. Now you're thinking that, well, there's forces on this, so imagine if I have a beam on some kind of wall and I'm pushing down with a lot of loads here. So just intuitively, if this is fixed, as we said, so then we assume that this beam is not moving. Well, something's got to be preventing this from moving, and the only contact it has with anything else in the world really is this connection here. So we're going to really care about point A and what forces the wall is giving the beam that are counteracting this distributed load, such that this beam doesn't translate in any direction and then also doesn't rotate. So immediately, the first step always, after seeing this, understanding the problem, is to write out all the forces that haven't been shown. Because they've given you this, but they're not going to write down every force you could possibly have. And as we know, there won't be any here, but there'll be a lot at A. So going off what we know about fixed connections, those can give reaction forces of vertical force, horizontal forces, and moments. So we need to write down all three of those. So we can test all three to see if there are any of each in this problem. So I'm not going to draw it straight from this point, but there's going to be some kind of reactionary force, and we're just going to arbitrarily assume that it's positive in this direction, although we might get a negative value for this, which means it's going down. It doesn't matter for our purposes. We'll have R2 of some kind of horizontal reactionary force, if there is one, and it's going to be the same positive as this. And also we're going to have some kind of moment reactionary force, possibly, and we're going to arbitrarily say that clockwise is positive. So now we have how many variables? We have Q1, L, R1, R2, and M. So now we need to derive some equations so that we can start solving for almost all of these variables. We don't need to solve for L because that's a constant in this case. We also don't need to solve for Q1 because it's a constant. But we care about these in relation to these values. So let's first write down Newton's laws, because it's easiest to start with caring about these forces before we look at this moment. So we need to, because this is not translating in any direction, we're going to write down equations that show that this doesn't move in the vertical direction, doesn't move in the horizontal direction. If that's true, it's because there are no forces in that direction. So first we have in the horizontal direction, the net force is equal to 0. And that means that we look at the only horizontal force we have in this situation is R2. So quite intuitively, if there's no forces on this beam in the horizontal direction, the wall is not going to have to give you any reactionary force. So R2 equals 0. This might seem like a very pointless step, but it's very important. Once we might have, let's say we have an angled force, then this is definitely not going to be so simple. So we should keep the standard of always writing everything down. Now let's look at the Fy in this direction. That's going to equal 0 too. What does that equal? Well, we actually have more in here. We have the distributed load, which is in a vertical direction. We also have this reactionary force. Notice that the arrows here are pointing down. We've already decided that our coordinate plane has the positive being up, so these are going to be negative. This is positive because you wrote it as positive. So 0 equals R1 minus, now what is this load? Each of these is Q1 down over this distance. For a completely horizontal distributed load, all you do is multiply the value of this function by L. So it's Q1L. 0 equals R1 minus Q1L. That just means R1 equals QL. So already, even though we haven't even finished all of these, we've already discovered what this is. This is Q1L. and this is 0. So now we care about moment. Same kind of equation, given this direction positive, the net moment, and here, so for moments you have to choose, when you do this equation you have to choose a point about which you do the moment. It's usually, you care about relevance, so if there's some point in this body which can possibly move, that might be a good place to check the moment, but also you might do it more strategically to try to get rid of extra forces you don't care about. There are two forces on this point, R2 and R1. If you do a moment about a point, then you don't care about the forces there, because as in torque, it's based on R cross F. If the distance from the point is 0, then there's going to be no torque, no moment. So we're going to strategically pick point A to do our moment equation. And it turns out that that actually makes sense intuitively, because you might care about whether this beam will rotate about point A. Equals, well, there's a moment from here, and then there's this moment given. Like we said, R2 and R1 are multiplied by 0 because they're right at the point. So they're going to equal 0 in the final equation. You're going to care about this moment, so it's in the positive direction that we indicated. And notice that you don't care about a distance here. I just said that torque is related to R cross F, but we're already giving you this value t, so you don't care about the force or the distance from the point of rotation that this m is derived from. You just use this variable. But you do care about this one. So how do we figure out a moment for a distributed load? Because it's not, we don't have a set radius or distance from the point of rotation by which to calculate. Well, distributed loads can always be imagined as a single load. So just intuitively, before we get much into the ideas of centroid, for distributed load it's really easy. It's all uniform. So you can think of it as right in the center. It's the equivalent of some kind of force down. And that force, if you get rid of this distributed load and just put one here, that one force needs to equal the total value of all of this. So we know intuitively that this is a L/2 distance, and we already said that this whole distributed load has a total force of Q1L. So this force itself would have a Q1L force, and this is L2, so we can write that as positive, because this is tending to rotate this around our given direction. Q1L times L/2. Now notice that there's two positives equals 0, so in fact our moment here is going to tend to be in the opposite direction of what we wrote, which is fine. We have standards, and we're going to always be confident that if it ends up being negative, if one of these ends up being negative, it goes well with our expectations. So m here, solving for m, it's going to be negative Q1 L squared over 2. And so we have all of our values. And what is the significance of this? You have them based on variables. You know, if you can find out the exact value of this distributed load, you find out a lot. If you find out the exact length of this distributed load, of this beam, you can find the moment, reactionary forces of all of this. Why do you care about reactionary forces? Well, you need to make sure that your fixed connection is strong enough to withhold whatever distributed load you might have, say snow on this beam, rain, winds, anything. Well, you're going to make this connection strong enough, so you need to make sure that, well, R2 doesn't matter. You need to make sure that R1 is strong enough. You make sure there's some sort of moment connection that is large enough to accommodate Q1 L squared over 2.